All right, ionic equations and precipitation reactions. Worksheet, do all of it. And this is a way amazingly important topic. And what's going to happen is, this is what becomes of the Monday quizzes. Like the Monday quizzes, you know, you have to predict chemical reactions, and then you're going to have to write them in net ionic equation form. Now, I don't know when you'll be seeing this video. I don't know if I'll play it. I don't know yet when I'll put it in the sequence, because as of right now, you haven't even had a Monday quiz. We had to predict the products. So this will probably be something that will be a couple of weeks from when I'm doing it right now. I don't know when that will be when I show you this video, but there's some stuff important about it. I might hold off, and you might not see it until after you see the next section. This is 412. So when you see it, you may have already done some sections after it. I can actually do that. I can teach the other things and then say a little bit about this. But now it's the big thing. Okay. All right. So there'll be some stuff in here that you have to remember, some little patterns and trends. It's not so hard, but you need to practice a lot of different examples. Okay, what in the world do we mean by ionic equations and precipitation reactions? Oh boy. Okay, well, here's a picture I was going to show you in 412. You see that first one? It shows, here's a chemical reaction. Magnesium chloride reacting with silver nitrate to give you magnesium nitrate and silver chloride. Now, let me even just go on and say now, how will this appear on an AP exam question, or how would it appear on the Monday quizzes? It would say something like, an aqueous solution of magnesium chloride is combined with an aqueous solution of silver nitrate. Okay, that's all they'll tell you. Magnesium in words. It won't be in symbols. It'll all be in words. So anyway, so what you gotta do first, you have to think about your solubility rules, and you gotta know. What if I have them somewhere near me to hold up, Mr. Hogg? Oh well. Where's little Hogg? Is he on the floor? Oh well, he's somewhere. Well, hopefully he's in your head. You've got him somewhere near you. But when you look it up, you'll see that halides, all the halides are soluble except for, and you see the little picture there of the hog, mercury 1. You see his little copper earring, copper 1. You see his silver necklace that he has as well. And you see he's eating that PB plus 2 cans of peanut butter. So, obviously that one is aqueous. And silver nitrate, you know it's aqueous because all nitrates are aqueous, dissolve. Now, the thing is, when they tell you in a question, two aqueous solutions of magnesium, an aqueous solution of magnesium chloride and an aqueous solution of silver nitrate are combined, they're telling you actually right there they're aqueous. So the question itself can actually give away the solubility rules. Like, oh, okay, that might help you remind, oh yeah, all nitrates dissolve. Oh yeah, all chlorides except for what are those for? So that might help you out. Now on the other side of the equation, of course, you'll have to predict this on your own completely. Now that we give it to you on the paper. And magnesium nitrate is aqueous, all nitrates. But silver chloride, no, it's a solid. Remember, that's the one that will precipitate. So what that means, when I say precipitation, I mean, it's just so bad that I might have some chemicals around at some point. I do have some. I'll have to see if any can show you this. But it's something undissolves. It's really amazing. So like, say this is completely, looks like clear water. This is completely clear water, transparent, nothing in it. Looks like water, but we know it's not really water. But still, you can't see anything in there. It looks transparent. You mix them together and suddenly you see this white cloudy stuff in the water. If you wait for a while, it will sink down to the bottom. If you put in a centrifuge, you'll see a powder at the bottom. It's silver chloride powder. It's a solid. So precipitation is kind of like saying in chemistry, something undissolves, all right? So pretty weird, pretty amazing. The silver finds the chloride and they come together and make silver chloride. Okay, so I drew a little diagram to say a solution of magnesium chloride and solution of silver nitrate. That is not really how they are, and I know I've told you that in this chapter already. That's not really what they look like because they're not together. They'll be split apart. Really, it looks more like this next picture on the next block. If you look at that one, and you see the magnesium and the chlorides are all split apart. Dissociate is the word for it. They're dissociated. All right, I did it. Okay, I was trying to fold this back. And the silver and the nitrates are also dissociated. Now, of course, you're going to have 2 chlorides for every 1 magnesium, if I did the math right with my drawing, and 1 silver for every 1 nitrate there as well. Okay, so an ionic equation is the equation where you just show all of the chemical compounds dissociated, broken up into their ions. So magnesium chloride is truly Mg plus 2, and you'll get 2 chlorides with it. All right. Now, for silver nitrate, you will get. Now I balanced this equation right here, or did I? Oh, that side's different too. Also right. Okay. 2 silver plus 1 ions, 2 nitrate ions. We get 1 magnesium plus 2 ions. Now on this side, so everything that is aqueous will break up as long as it is not a weak acid. And I'm going to get back to that in a minute, but we don't have to worry about it right now. But you'll see this. So any ionic compound, metal and a polyatomic ion, or metal and a non-metal, if any ionic compound, metal, non-metal, metal, polyatomic ion, if any of those are aqueous, they will always be broken up. But here is an ionic, okay, I'm sorry, I'm jumping ahead. So 2 nitrates, see there's 2 NO3s. Now here's an ionic compound, metal and an ion and a negative ion, chloride, and it does not break up because it is a solid. AgCl solid. That one will not. Now, everything else is aqueous. It means it's dissolved in water. That means it is surrounded by water molecules. Remember I told you about how on the water molecule, the oxygen has negative ends because of what's called lone pair electrons. But this side is negative, slightly negative. Not quite -1, but somewhere like maybe negative, I don't know, 0.35 or something. But on this side, it'll be positive 0.35 there and there. You might even sometimes see a symbol that looks like this, and we'll talk about it later on. That's a Greek letter delta, but that little delta symbol plus means that's the positive end. Delta negative means here are the negative ends of each of these bonds. Okay? But delta represents a number between 0 and 1. So it's not quite +1 or -1. But anyway, okay, don't worry about all that. But the point is, the positive part of water will attach around, which is the hydrogens, will attach all around the chloride. The negatives all around magnesium. You have billions of water molecules, to just completely surround all this stuff, and it dissolves. Okay, that's called the ionic equation. Now, spectator ions. Okay, notice this. Now, the only thing that really changed in this picture, remember in the beginning, you started off with just this. You had magnesium and chlorides dissolved. Here you have silver and nitrates dissolved. Well, in the end, look at what happened. You have silver chloride, but look at the magnesiums and the nitrates. They're still dissolved. They're just the same as they were back here. The magnesiums here are just like they were here, still surrounded by water molecules. Nitrates here, just like the nitrates in this container, still surrounded by water molecules. They're unchanged. They did nothing. They're called spectator ions. So spectator, well, you see it on the paper, but spectator, like in a football or baseball or basketball game, they said the spectators were not involved in the actual game. They didn't influence the game. They were just there. They're okay, spectators. Now we know that playing home field advantage by screaming, especially basketball games, the spectators could have an effect. But we will say they don't have an effect. Like maybe like if they're closed off in this luxury, glassed-in, air-conditioned, nice room. They have those too. So some of the games very expensive I've never got. I got to go one time to one of those in a basketball game. It was amazing. At the Staples Center, that was incredible. That was somebody knew somebody that knew somebody or whatever. Hey, I got to go. I don't know if you ever got a chance, but if you ever do, that's a cool thing to do. The VIP rooms or whatever. There are a lot of them actually, but oh well. Back to this. Okay, so spectator ions are anything you see on the left and on the right unchanged. Magnesium plus 2, magnesium plus 2. So it's a spectator. Now I'm going to just circle it for right now. All right, and then anything else? Nitrate and nitrate was not involved in the chemical reaction. Okay. Oh, I put a line already. Well, okay. So we do. If you were asked on the AP or by me to write the ionic equation, you would have to write this entire thing. But if you were asked to write the net ionic, and this is what they always expect on AP, they'll say they're going to ask you to write the net ionic equation. What happened? In the past 80 years, 80, 85 years of AP exams, there used to be a section where they would give you 8-word equations. They wouldn't even give you, they would not ever tell you the products. They just give you the beginning. Like aqueous magnesium chloride solution is combined with aqueous silver nitrate solution. That's all they write. Or they'll say something like copper metal is heated strongly in oxygen. Copper plus oxygen. Oh, it's going to be a copper oxide. Okay, they would only give you something like that. And what you have to do is write the entire equation and put it in net ionic form. Now, they did that for many years. I'd say probably they did that for like 70 years. Okay, maybe more than 70 years. Then, in the past 10 or 15 years, what they've done is they shortened it. Instead, they had 8 equations. I'll tell you, and you only had to choose 5 of them. So you only had to do 5 net ionics on every exam. Then they changed it down to only 3. Okay, so that but it was 3 that you had to do. You didn't get an option anymore. They just gave you 3. They still use the same choices as they had from all beginning. There might be a couple of real rare ones that are tough that they don't ask that much, but hey, you got to know them, and I've taught them, and we'll drill them and practice them in case they ask it. But 3, they went down to 3. Now on the AP, they don't have a dedicated section that say, hey, here's the equation question. But what they do is they say that on 3 FRQs, you can expect 3 or 4, is what I heard. You can expect 3 or 4 net ionic equations somewhere. And they could even work it into multiple choice as well. A lot of stuff that you learn, when you learn the solubility rules, you learn how to predict stuff, you learn all this net ionics. There's a lot of skills that you get that will help you to answer other multiple choice questions. So all these drill quizzes we're doing, I would say they're going to be worth more than just the 3 or 4 equations that are going to be on the AP exam. There's a lot of other stuff. The colors of these things we get to know. Hopefully we'll do labs. See, all of this, there are lab observations as well. If we end up for some reason being closed down and a Zoom school all year, I'm going to have to get some chemicals and show you videos of chemicals and stuff so you'll know these colors. But I don't think AP will expect. Well, I don't know. We'll see. All right, here we go. So spectator ions are those ions that are not involved in the chemical change. And then when you write the net ionic, it is like saying, okay, when you get a paycheck and it says, here's your gross, this is how much money you made, your hourly rate times that number of hours you worked. There's your gross. Then minus, then they underneath it, they subtract the income taxes stuff or whatever, what they took out for taxes or for Social Security or all the other things it might be. You might, who knows what it is, that they contribute to something. But anyway, they take out all the minus, and then you say the net pay, and that's what your check says. So net is like what is left over after all this other stuff is taken out. So, once again, if you have to write an ionic, this is what you write. But if you have to write the net ionic, interestingly, watch this. If I do this, magnesium gone, nitrate gone, nitrate gone. Guess what? That, the only thing wrong with it now is we have 2, 2s, and 2s. I'll tell you about that in a second. So if you just put lines through it, that would count as an answer acceptable on the AP. You don't have to, because a line through something means it's not there. So that means, it's chloride plus Ag plus 1 gives you AgCl. Well, I almost put the number. Now, the only thing is, in this particular equation, I've got 2's. 2, 2, and 2. Well, that will be reduced to 1, 1, 1, and you have to have it reduced. And they're now asking you to balance them. That's another thing they didn't do. So, from 70 years, they gave you 8 equations, you choose 5, but they didn't make you balance any of them. Now, they give you 3, or maybe it could be 4, I've heard, 3 or 4, and you're going to have to balance them, okay? Now, when it comes to that about balancing, what I tell everybody to do, when you're writing out your ionic equation, don't write the numbers. Don't even write these numbers here. 2, 2, 2, 2. Wait till the end and do it. Actually, okay, so let me say it again. If you're aiming to write a net ionic, then do not bother with trying to balance it along the way. Don't worry about 2. Just put MgCl minus, AgNO3 minus, MgNO3 minus, and then that one doesn't break up. And then at the end, if we're going to balance it now, do I need to balance it? 1 chloride, 1 silver, and we're good. And there's something else about a net ionic that I need to tell you. And it really needs to be added here. A net ionic, because we didn't have to balance it when I first made these notes a long time ago, we didn't have to balance them. So, I believe I only taught for a couple of years, maybe 1 or 2 years, where we had the old way, okay, and then it changed. But here's another thing: balanced by number of atoms and balanced by charge. And you're going to hear about this in an upcoming lesson as well. But all right, so what it means, what is your total charge on the left? -1. All right, so 1 at chlorine, 1 silver, 1 silver. 1 times -1. -1 and +1 gives you 0 charge on the left, and AgCl has 0 charge. Okay, another thing really important is when you write down AgCl, I know when you're playing around and trying to figure out formulas, you might have put +1, -1, okay, or +2, -1. I do that all the time, but you cannot have it in a net ionic. It cannot be there. If you put +1, -1, that's counted wrong. Okay, the only time you put charges is when something has a charge. Cl -1, Ag +1. Yes, has a charge. Yes, charge. This is neutral. I know, +1, -1, well, that's neutral. Yeah, it is, but no, you're not allowed to. Because if you did have the only time you put a charge on something like that is if it were a polyatomic ion or something called a complex ion. What in the world is that? It's going to be more fun that comes later on, not now. Okay, so balanced by number and by charge of atoms. Number of atoms on each side and by the charge on each side. They have to all balance. Okay, long time. Now, you almost never see balance by charge as a factor. The only time it really comes into play is when you're doing redox equations, usually, and we're going to do that. We're going to show you that for sure. Okay, later on. Okay, so here are some samples. And I wrote this last bit. In the net ionic equation, only the substances that undergo a change are included. This may be solid, liquid, gas, or even aqueous in the case of weak acids and bases. Oh, yes. Okay. I better tell you this before it pops up on some example. Okay. And, like I said, if you've seen some in a different order, if you've seen the videos, maybe you heard some of this already, but I think now I'm going to go going really in depth about this. Okay. All right. There are 6 strong acids. And what are they? I know I've told you a couple of times. Well, I don't know if you've seen those videos yet, but I think you've at least seen one video where I said that. They are hydrochloric, hydrobromic, hydroiodic, the friendly acid. Then you have nitric acid, sulfuric acid, and perchloric acid. Okay, what does it mean if you have these acids? Well, if you're writing an equation, like hydrochloric acid is mixed with sodium bicarbonate, write the reaction. Okay, hydrochloric acid, strong acids completely, well, we assume 100% dissociation. They completely break up. All right, we'll say that completely. Okay, so HCl, if I'm writing HCl in an equation, the ionic will be H plus and Cl minus. Okay? If I'm writing HNO3 in an equation, whatever, I'm going to write H plus and O3 minus. Okay. Now, H2SO4, it's okay to put 2H plus and SO4 minus, but technically it is H plus and HSO4 minus. So, but I've seen both acceptable. So we'll just wait and see when that pops up. But sometimes, oh, and there's one more thing I gotta tell you as well. Okay, so that is the best way to do it. What I've always heard, but it's okay to put both, and they just say this or this. But just remember, the first H pops off. Now, so these are strong acids. If you have any other acid, you do not break them up. It's really strange. HCl aqueous is H plus aqueous, Cl aqueous. HNO3 aqueous is H plus NO3. But let's say you have vinegar, which is HC2H3O2. Acetic acid is another name for that. Hydrogen acetate. Another way to write it is CH3COOH. Now, in this, what could happen is you could think, well, can the this plus whatever chemical in an equation, could that break off H plus? A little bit can, but we assume that it does not break off. So what do we do? If we have this aqueous in an equation, we leave it all together because it's a weak acid. Only the strong acids dissociate completely. So not this one, not this case, would you get CH3COO -1 and H plus? No, we're going to assume it stays together. Now, I can tell you another example. C12, H22O11. You don't need to know that. This is table sugar. NaCl. This is table salt. When I put salt in water, it breaks up into Na plus and Cl minus all around through the liquid. But when I put sugar in water, okay, well, I guess I could have put solid here, and then on this side had H2O, whatever. When I put sugar in water, and then they're not going to ask you about sugar. Don't worry about that. But when I put sugar in water, guess what? The formula stays C12H22O11, but aqueous. The water molecules surround the sugar molecule, intact. So it is not dissociated. So sugar dissolves, but it does not dissociate. Okay? Sodium chloride dissolves and it dissociates. So NaCl solid is solid salt. In water it becomes NaClAq. But we know that NaClAq, this would mean, if you see NaClAq, that means it's dissolved. Like you have a 0.1 molar solution of NaClAq. That means it's dissolved. But what it really means is this. It doesn't mean that. It means this. They're dissociating. So just keep in mind, this is called a covalent compound. It dissolves, but it does not dissociate. Okay. Wow. So I am giving you a lot of details here. And all right, there's one more really picky, crazy little thing that you need to know. And I usually wait till later to tell you, but we'll see if anybody can remember this today. Concentrated acid. A concentrated acid means for these strong acids, HCl, HBr, HI, HNO3, HSO4, HClO4. Or how about, I'll talk about salt for a minute. This is easier. How can I make concentrated sodium chloride solution? I've never heard that term, but because usually we call it saturated, but it's the same thing. All right, what you do, you take a glass of water, you put some salt in it, and you stir it up, and you don't see the salt anymore. If you drink the water, you'll taste it, okay? So salt is gone. But then you add more salt, and more, and more, and more, and you keep doing it. You keep stirring it up, and watch it, and you keep doing it, add more and more salt until you see some salt at the bottom. When you see some salt at the bottom that is not dissolved, you know that now anything you add it's gonna just sink down to the bottom. So all the water molecules are all surrounded. They're all occupied. They're all surrounding sodiums, or they're surrounding chlorides, and there's no more that can dissolve in that water at that temperature. Okay, changing temperature can sometimes change that as well. But okay, so saturated or concentrated. So a concentrated acid means if I have concentrated HCl, you will never play with that. There's one lab that we do where you need to use concentrated nitric acid, and I do that when I've done that lab before. We have a fume hood, and in our new room we have a great looking fume hood. It's a glass chamber where you can do a reaction behind it. We do it in there, and I have like two or maybe four, maybe two groups. 4 people at a time can stand up and watch as I mix that into there. But I do that for you on that part of the lab. I don't want you to come near any concentrated acids. They're really, really dangerous. But what that means is concentrated nitric acid means I have no more HNO3 will dissolve in that water. That's what it means. It's very strong acid. Okay, well, here's a strange thing, a strange little long story to tell you this. If you have concentrated H2SO4, it does not dissociate. Now, in order to break up into positive and negative ions, you have to have water molecules, okay? And an acid is only an acid, AQ, when it's in water. We know that. Well, here's the thing. Unlike the other acids, when sulfuric acid is aqueous, when you dissolve as much H2SO4 as possible in water, what happens is it is 98% H2SO4 and only 2% water. Isn't that bizarre? So you have almost no water at all in concentrated. And so what happens is H2SO4 concentrated does not break up. It stays H2SO4AQ as if it were a weak acid. But boy, it's not a weak acid. You don't want to put your hand in there, because even the little moisture in your hand, a small bit of water added to this, and it will just violently react. And of course, it will all break up. It will start breaking up. All with the water will break all of it up. So pretty neat thing, pretty crazy thing. Okay, so I just wanted to tell you that little bit. So who breaks up in a non-ionic? What chemicals do you separate into positive and negative ions? Only if it is soluble ionic compound. So look at the solubility rules, okay? Or if it is a strong acid, then you break it up into positive and negative. But if it's a weak acid, you do not, okay? Or if it's obviously if it's a solid or a liquid or a gas, you don't break those up either, okay? And if it's a concentrated sulfuric acid. Okay, so let's try to do some reactions now. And here we go. And let me see. Oh, okay. 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 I have my pages mixed up a little bit. Letter A. It says aqueous calcium hydroxide and aqueous magnesium chloride are combined. So aqueous calcium hydroxide. So you're going to write down CaOH -1, +2. Okay, aqueous calcium hydroxide. All right. Well, I'll come back to that in a minute. And aqueous magnesium chloride. Chloride -1, magnesium +2, MgCl2. Okay, now aqueous. They told me it's aqueous, so I told you how that could be a little help for you to remember your solubility rules. Hydroxide. What's the rule say? None of the hydroxides dissolve. When I hear say hydroxide, none dissolve except for the camel with straw on his back, or of course group 1 or ammonium. So yeah, that one will dissolve. Okay, magnesium chloride. Yes, it dissolves. Okay, what will you get? What kind of reaction does it look like? A double replacement. Calcium goes with chloride, and magnesium goes with hydroxide. MgOH2. Now, solubility rules. Calcium chloride, is it going to be aqueous or solid? Okay, calcium chloride will be aqueous. Okay. Because remember, the only chlorides that would precipitate are silver, lead 2, mercury 1, or copper +1. Okay. Now, magnesium hydroxide, aqueous or soluble, it will be solid. I said aqueous or soluble. Aqueous or solid, sorry. It'll be solid. Because none of the hydroxides dissolve except for the camel with straw on his back, calcium, strontium, barium, group 1, and ammonium hydroxides. Okay, now, so that's the that's the molecular equation. And by the way, you want the molecular equation if you're ever doing stoichiometry. You pretty much just need the molecular equation. And that's what, and they give you that pretty much all the time in AP on problems. But all right, for the ionic, did it say to write all of them? Yeah, the ionic equation would be everything aqueous. So that is a soluble ionic compound. Ca and OH negative. I'm sorry, I should write my negative one like that to the right. Plus a lot of people, even books, instead of writing -1, well, they write 1 negative, or +2, they write 2 positive. That might be kind of more of an official form, but I always do it this way. So they won't care about that. Okay. So chlorides. Now I'm not balancing them. You would get 2 chlorides. You would get 2 because I know I'm going to have to get the net ionic. Oh, but you know what? I better do that. I better. Okay, yeah, I better put the 2. I'm just thinking about that right now on my worksheets. On my worksheets, I don't know if I did that for the ionic, but it just occurred to me right now that, wow, what if they were to say write the ionic equation? Well, then if they said write what bad Bella, what are you crazy? If they said write the ionic equation, you do need to show them balanced on that. But I'll just say this, and that one will not split up because it stays a solid. If you just have to write the net ionic equation for this, then I wouldn't bother with that. When you do the Monday quizzes, don't bother with writing these numbers here. No. It'll just take you time. Okay, so now to get the ionic equation, I'll say, the net ionic, anything that's on the left and on the right unchanged gets crossed out. So the calcium ion, instead of crossing it out, I'm going to underline it. That goes away. The chlorides and the chlorides go away. So you're left with 2 OH negative plus Mg plus 2 to give you MgOH2. And you know what? I actually am glad, well, on this one, I do want you, on this worksheet, I want you to balance them. Again, when I made that worksheet, I don't think it was required to balance at that time. But at the end, you would balance that out. So on my assignment, all it's going to say, well, you know what? I might be wrong. I might be asking you to write this, to write all 3. Yeah, so you will have them balanced. But if you do, when you do the Monday quizzes, I can tell you, I do not want you to go through and write down and balance 5 equations all the way through. That will just take a lot extra time. All I care about is, can you get the products, and then can you correctly find the net ionic? If you can get that, that's great. You can always go back and then balance it, okay? All right, now, let's try another one. Let me just watch the time here, okay? So, solid sodium hydroxide and aqueous sodium chlorate. I think I can get all these done here. All right, solid sodium hydroxide plus aqueous strontium chlorate. Sorry, I read that wrong. Strontium chlorate. Well, okay. Aqueous. I forgot to tell you one thing a moment ago, but, well, on the last equation we just did, it was solid magnesium hydroxide. It was solid. If it had been something like produced, like, say, calcium hydroxide or something, you started with calcium hydroxide. But say if the thing that you produce was soluble, it was aqueous, if everything is ionic and aqueous, then when you make an ionic equation, every single thing is a spectator ion. If that ever happens, then what that really means is no reaction. Because if everything is dissolved before and nothing changes and everything is dissolved at the end, that is a no reaction. And the AP will never ask you a no reaction. Now, I might, like I told you, give you an equation. You might see something pop up on multiple choice or whatever, which would not be a reaction. Okay? And so you need to know that. But, okay. Anyway, back to this. So, for this one, you'll get sodium chlorate, NaClO3. Oh my goodness. And you'll get strontium hydroxide. Can you see what just happened? Or what's going to happen? I was trying to think of an example, and I don't have to because here it is. Oh, no, it's not here. It's not here. Okay, good. Okay, aqueous. Okay, so this is solid. This is aqueous. This one is going to be aqueous. All chlorates are soluble. Hydroxide is also aqueous because none of the hydroxides dissolve except for calcium, strontium, strontium, and barium. So it does dissolve. So from what I told you a moment ago, it would almost look like, I almost fooled myself and thought this was one, but it's not. This is a reaction. So when I looked at this, I almost thought, oh, two things are aqueous and they're both going to split up. In my ionic, I'm going to get sodium plus 1, chlorate negative 1, strontium plus 2, and 2 hydroxide negative 1s. But look at what I started out with, a solid. And in the ionic or net ionic, a solid does not break up. It does not dissociate. Oh, that will. Sorry. Strontium chlorate, yes. Okay, so what I always say is you don't have to write aqueous for all these things, but I would, if something's a solid or liquid or a gas, I would probably write it down just that way you don't mix yourself up, because if you've forgotten, you might have accidentally split that one up. So that helps me to know, hey, that's a solid. You know, you don't have to write all these even. It might be good on the first step to do it, but down here you certainly don't have to. Okay, now anything, spectators, strontium and strontium, and then chlorate and chlorate. And so there is your reaction. I didn't even balance it up there. That's why I had the 2. I left off the 2 there, but I did put the 2 there. Sorry. Well, you can put a 2 there. But anyway, you get sodium hydroxide solid. And then it turns into sodium plus hydroxide. So, in other words, the only thing that happened in this reaction was the solid sodium hydroxide just dissolved in water. The other chemical didn't do anything with it. That's all it was. That's a dissociation reaction right there. A dissociation reaction. A solid just turns into the positive and the negative ion. Okay, that was B. I didn't label it. Then there's one more left. And then you're ready to do all those on the paper on your own. So here it is. The last one says, come on. I gotta go. Okay. I got a lot of things going on here. Calcium chlorate and hydrochloric acid. So calcium chlorate plus hydrochloric acid should be aqueous. Yeah, you should say aqueous I'll tell you aqueous, okay? I left that word off. It should say aqueous calcium chlorate is mixed with hydrochloric acid. Okay, hydrochloric acid. Whenever something says acid, it is aqueous. It is, okay? Because you have to have water in order to get aqueous. All right, so here we go. I'm taking a long time here on this one. Calcium goes with chloride. CaCl2. H will go with ClO3. HClO3. This one's going to be -1. That's going to be +1. Now, so you ask yourself, again, that one had to be aqueous. I should have given you that. Calcium chloride is aqueous. Because, once you mix them, they're in water. This is produced in water, and all the chlorides will dissolve, okay, except for those 4. Well, HClO3, it is also aqueous. All chlorates are soluble. When I write the ionic, Ca plus 2 plus 2 ClO3 negative, that will split up. It's an ionic compound that's soluble. H plus and Cl will break up. because it is a strong acid, and strong acids completely break up. They dissolve, but they also break up into positive and negative ion. Calcium chloride is also soluble, so it will break up. Well, I'll put 2 Cls. Okay. HClO3 will not, because it's a weak acid. Remember. Now, HClO4, perchloric acid, is strong acid, but chlorous acid is a weak acid. It stays together, like sugar, I told you. It doesn't break up. Okay. All right. So, even though it's dissolved, it's staying together intact. So then we go over here, anything to cross out. Chloride on the left. I'll do it with the underlining it. Like I said, if you have to write the ionic as an assignment, you better show the whole thing. Don't cross anything out. 2 Cls, 2 Cls. 2 chlorates here. And, all right, calciums are going to go away. So you're just going to have the 2 chlorates and then the H+. I guess I'm not all the way balanced, right? Because I would need to. Yeah, I'd have to balance this equation to get it all balanced. But chlorate would give you plus, H+, will give you HClO3. That is your net ionic equation. You produced a weak acid. All right, so do those equations and fun with net ionics. And this is a skill that will take you a lot of time to develop over weeks and weeks till the AP. And oh boy, there's more for me to tell you about that later on. But for now, that's all.